So we're gonna talk about energy in the electrostatic field. And in essence, the thing that we're gonna get to is that the field, the E field, holds energy. Essentially. And we've already talked about that a bit when we discussed voltage. So when we discuss voltage, if you have a charge or a field, and then you bring a charge in from infinity, you need energy to bring that charge in from infinity to some point. And that energy required to bring that charge in is essentially the voltage, charge over Q. This is QT. So you're moving a charge QT from infinity to that particular point. And every particular point here is going to have a different sort of energy that is required. Right, so if you move the charge from to P2, you'll have a different kind of energy that's required. That energy divided by the charge gives you the voltage at that point, P2. Right? So in a way, there is some energy field associated with the electrostatic field, and that is the voltage scalar field. The way to think about it is that similar to a spring. If you have a spring and you push on the spring, you're an external force, and you apply an external force as an external, someone external to the system, you apply work into the system, and then you compress the spring. So you exerted energy to compress the spring. So you gave energy to the system. The question is, where is this energy stored? People would say for a spring, hey, it's stored in the spring. So energy is stored, is stored in the spring itself, the tension of the spring. And then when you release the spring, it kind of like releases. Same thing with the electrical field. If I have like a positive charge and I bring a positive charge in, the spring in this case is the electrical field. So this is the perspective that we take, is that yeah, I exerted energy to move those two charges closer to each other, but where is this energy? Is this energy lost? Is this like friction? Where I exert energy on something and just heat it up, or is this energy stored somewhere to be released later? Yes, it is stored somewhere. The question is, where is it stored? So the analogy here is that the tension in the spring is the field itself, right? So the field itself carries energy, and then when I release the charges move away from each other, and the field dissipates. So you bring the charges close, the field builds up. You release the charges go away from each other, and the field dissipates. So clearly, the energy is stored in the field itself. The question is, how do we see that? How do we prove that? Intuitively, we can think that it makes sense, but we need to show how can we tie up energy to the field itself. Okay, and over this lecture and the next lecture, we will show exactly how is it that the field carries energy. Essentially, we will quantify, show how do we calculate energy in the field if we know the field, essentially. Yeah, by the way, the field also carries momentum, right? But this is something that we're not going to study this course, but it's not just energy. The field, the electromagnetic field, is a complete physical system, dynamical system. So it is like any real system out there, like masses and matter. It's going to have momentum and energy. That's why people don't only talk about the energy of the photon, they talk about the momentum of the photon. Okay. So the first introduction into this, into the energy content, talk about that later. first introduction to the concept of energy is in the scalar field of the electrostatic field, the voltage. So even the units for the electric field are volt per meter, right? So this is energy per unit charge. Right? You get the energy back by multiplying by meter, integrating over a distance, and then multiplying by charge. So this is one representation. Up until now, we have three representations of the electrical field. So in space, at a point P, we have three different representations of the same thing. So the electrical field, it's its own thing, and we have three different ways of representing it. I think we mentioned the analogy in the past. It's like a wind field. Wind field. The field is its own thing. It exists regardless of how we measure it, but we can decide to measure it by either measuring, force or pressure. So put an object in the wind field and measure the pressure of the wind. Another way is putting like some device that measures the volume of air. So volume of air per second, for example. So this is one way of measuring the wind field, by measuring the pressure at every point of the wind. Another way is measuring the volume of air per second at a point, have some apparatus that measures how much mass of air passes, volume or mass, let's say mass of air passing every second. And a third way is to kind of take an object and move it across the wind field and measure how much energy you need to move that object, right? Energy required to move against the wind field. So those are all three different valid ways of assigning a number at every point in space for the field. But those are not three different fields. It is three different quantifications of the same thing. So same thing here, we introduced like a lot of things. We have introduced three main things. We introduced E, we introduced D, and we introduced V. Those are not three separate, those are three separate measurements, ways to measure the same thing. And then we related D to E through the constant epsilon. And of course, E equals minus grad V. This is only true for the electrostatic field, by the way. Come on, go away. Because for the electrostatic field, curl E equals 0. Okay, so V, E, and D are different ways of measuring the same thing. And already one of them has energy in it. So it has joules per coulomb. Volt essentially is joules per coulomb. So it seems that's the early clue now. How do we get energy? Just multiply V by Q. So this is just a hint. This is a hint from the units. That how do you get the energy? If you have just V, just multiply V by Q. Okay. But let's dive into this. So let's review voltage. So if I'm going from point A to point B, I have a field. So going in the opposite direction. The voltage from A to B. So this is the voltage going from A to B. It's VB minus VA is essentially the work done. You are as an external to the electromagnetic system. You have a test charge here, or whatever charge, 1 coulomb, say, and then you need to apply work to move the charge upstream. So it's the work done over the charge that you apply. Okay, and this is equal, we said, minus A to B E dot DL, right? And then from E equals minus grad V. So from fundamental theorem of calculus, grad V dot DL, right? This equals VB minus VA, or V at point P minus V at point A. Same terminology. So that's what the voltage is. And then from here, it's clear that W equals let me call this test charge, or let me call this small q to indicate that it's a test charge that I apply or that I move. Okay, so W equals Q VBA. This is the energy required to move the charge from point A to point B. This is not the energy of the electric static field. We're not there yet. This is just the energy to move a charge across the field from point A to point B. Okay, so this is not the energy of the field yet. This is just the energy to move a charge across the field. Now the question is, how do we anyway construct the field? Right, fields come from source charges that from sources, right? So anyway, I mean, the only way to construct the field is to build up charges. So the way we figure out the total energy in the field is to just construct the field. So it's kind of like you have two positive charges and they're far away from each other. There is no field. And then you bring them back closer, use expending time energy, and now you have a field. So the total energy in the field has to be, because energy cannot be created from scratch, right? The total energy of the field, WE, has to be the energy that you exerted to create the field. That's the key idea. Okay. So if you imagine space, this is space, is empty, completely empty. So E equals 0 in here, right? Everywhere. This is the entirety of space. This is the border at infinity. This is a thought experiment, right? And then what you're doing, you know, the charges are beyond infinity. All the charges in the universe are beyond infinity. And then the idea now is we bring in the charges. What happens if I want to build it? How do I build a field in space? I start bringing in the charges. This is P1. I bring Q1 to P1. I bring Q2 to P2. I bring Q3 to P3. If I start bringing charges one by one, I build up an electrical field. Right? So I build up an electrical field. The question is, what is the total energy that has to, this all falls back to conservation of energy concept. What is the total energy that has to be stored in the field? It has to be the energy exerted to build the field. And the energy exerted to build the field is the energy required to move those charges from infinity to their respective points. This is how you calculate the total energy of the field. This is the approach that we're gonna use. Okay, so let's do this example. Let's start the process. So I'll draw it again. This is my universe, all of space. This is infinity. This is R equals infinity. And I start step one. I have a charge Q1. This charge, I move it to point P1. Okay. The question is, what is the energy required for that charge? Yeah, what is the energy required to move the charge? Well, this is the first charge that we're moving into space, right? Because this is the first charge that we're moving into space, there is no electrical field. Initially, E1 equals 0. There is no electrical field. This is the first charge we're moving into space. So there is no electrical field, really. So W1, what is W1? W1 is the E dot dl from infinity to P1. But initially there is no electrical field in the universe, in space. So W1 equals 0. Right? So W1 equals 0. The first charge we bring in is free. Does not require any energy because there is no field opposing it. Okay. What about now 2? I have a second charge I want to bring in, Q2. Now I want to bring this charge in to point P2, from infinity to point P2. what is W2? Well, W2 is going to see the field due to charge Q1 that we already brought in, right? So what would be I guess you could do it through the field or we could do it through the voltage. What would be the voltage at P2 due to Q1? That's what we have to find first. So V at P2 due to Q1, we know this already is Q1 over 4 pi epsilon, the distance between R and 2, this distance, R1, 2, right? Volts. So this is the voltage at point P2 to Q1. Well, we know from the definition of voltage is essentially a measure of energy, measure that of the energy required to move a charge from infinity to that point. So the energy to move Q2 into P2 is going to be the charge Q2 times the voltage at P2 to Q1, right? So this is going to be W2. This is going to be the energy required to move charge 2. So W2 is going to equal Q2, Q1 over 4 pi epsilon R1, 2. Does this make sense? Does this have the right units first? Yeah, it has the right units, right? Because you just if you have R squared here, you have force, right? So you lost the R, right? It's like you multiplied by M. So this is force time meter, essentially. So this is work, right? So this is, and it has energy, has units of energy. Okay. Now we want to continue. So now we found W1 and we found W2. So we want to go on. I mean, ultimately, we can repeat this step forever. We can bring in charge Q3, charge Q4, charge Q5, charge infinity, whatever. But we want to stop at 3. We want to stop at 3 because we want to establish a pattern. See if we can establish a pattern. So if I now take charge Q3, charge Q3 is going to move to point P3. Okay. Now the question is, what is the energy now required to move charge Q3 to point P3? Well, to determine that energy, we have to determine the voltage at point P3. Because once you determine the voltage at point P3, the voltage quantifies how much energy does it require to move a charge from infinity to that point. But now the voltage at P3 is more complicated because now we have 2 charges existing in the universe previously. So now we have to find the voltage at point P3 using superposition, using the superposition of the 2 charges at P1 and P2. So the voltage at P3 now, so this is step 3, is going to be the superposition of the voltage due to Q1, 4 pi epsilon R13. R13 is this distance, R13, and then there is R23, this distance. Okay. So using superposition, this is going to be Q1 plus Q2 over 4 pi epsilon R23. Okay. And now the energy, total energy required to bring in the 3rd charge is going to be, you just multiply this by Q3. It's going to be Q3 VP3 equals Q3 Q1 over 4 pi R13 plus Q3 Q2 over 4 pi R23, right? And now finally, I want to stop at 3. We could continue this, but we want to stop at 3 and see the pattern. So the question is, we went 3 steps. We found W1, W2, W3. What is the total energy now required to construct this field? So now we have three charges in the universe. They have their own field. What was the energy required to construct this field? So the total energy, W, equals W1 plus W2 plus W3. W1 was 0, right? W1 was 0. W2 was this. Yeah, Q2, Q1 over 4 pi epsilon R12. W3 is this. So this is plus Q3, Q1 over 4 pi epsilon R13 plus Q3, Q2 over 4 pi epsilon, there's an epsilon there, R23. Okay. So this is the total energy stored in the field. Okay. Now, crucial point. The total energy stored in the field, ultimately, when we construct the field, should it really depend on how the order in which we bring the charges in? Meaning, let's say instead of bringing Qn first, and then Q2, and Q3, and then Q3, let's say I bring Q3 first, and then Q1, and then Q2. As long as I bring the charges into the same final points, it shouldn't matter. The field is going to be the same, right? So doesn't matter how you construct the field. It's like potential energy and gravity. Doesn't matter how you get to a certain height. You will always have the same energy at that height. So same thing here. It doesn't matter the order in which you bring in the charges. What matters is the final configuration. All right. Because what matters is the final configuration. We can do this. We can examine what happens if I bring in the charges in a different order. And then I know for sure, because the field at the end will be the same, that that energy should be equal. Because what matters is the final configuration of the charges. So I could calculate the energy by moving and bringing in Q3 first, and then Q2, and then Q1, essentially. So I can repeat this calculation and bring in Q3 first, Q2, and Q1. I don't need to repeat it really, because all I have to do in this equation, I'm substituting 1 for 3. So all I have to do is I can replace 1 with 3 and 3 with 1, and that's it. I'm done, essentially. Right? I get the same result. So if we rebuild the configuration using this order, you could go through it again, but you don't need to, because it's just a renaming of the charges, right? You now Q1, call it Q3, and that's it. So instead of 3, you put in 1. So I have here Q2. I have Q1 instead of 1, I put in 3, Q3, over 4 pi epsilon. Instead of 1, I put in 3. So this becomes R32. Let me set it up so that the smaller number is first. So this becomes R23. Plus, instead of 3, solve it with 1, Q1. Instead of 1, put in Q3. 4 pi epsilon. Instead of 1, put 3. Instead of 3, put 1. It becomes R31. This is the same, R13. Instead of Q3, put Q1. Instead of Q2, it's the same. 4 pi epsilon. R23 becomes R21. So this becomes R12. If you repeated the process, starting with Q3, Q2, Q1, you would get this equation. Now we said this should equal to this. So we can sum them up. What happens if we sum them up? 1 plus W plus W is just going to equal 2W. Okay. What is 2W? Well, let me collect terms. So let me collect the terms with Q1. So I think, those two terms has Q1. So let me collect them. Okay. And take Q1 out. So this becomes Q1. And now we'll see the pattern emerging. Q3 over 4 pi epsilon R13 plus Q2 over 4 pi epsilon R12. Okay. And then let me collect the terms with Q2. The terms with Q2 are this and this. And take Q2 out. Plus Q2. No, order always doesn't matter. Always doesn't matter. Because the field, it's like a spring. If you compress a spring from the right or from the left, it doesn't matter. What matters is the compression of the spring. So it doesn't matter what order you bring in the charges. What matters is the field at the end. Okay. So Q2, here I have Q1 over 4 pi epsilon R12, and then plus Q3 over 4 pi epsilon R23. A pattern is emerging. Let me take now those two terms. So plus Q3, Q1, Q2. So Q1 over 4 pi epsilon R13 plus Q2 over 4 pi epsilon R23. So an interesting pattern emerges. What is this? This is R13, so this is 1, 2, 3. This is R13 and R12. And then I have Q3 and Q2. This is the voltage at P1 due to Q3 and Q2. What is this? So here I'm seeing the distance from 2 to 1 and distance from 2 to 3, right? Sorry, the distance from 1 to 2 and the distance from 1 to 2 and distance from 3 to 2. And then I have Q1 and Q3. This is the voltage at 2 at the position of final position of charge 2 due to Q1 and Q3. And here we see the distance from point 1 to charge 1 to charge 3, the distance from charge 2 to charge 3. Then I here have Q1 and Q2. This is clearly the voltage due to Q3, or due to, sorry, Q1 and Q2 at position of Q3. So what this equation tells me is that W, and I can take the half to the other side, is just Q1 times the voltage at the location of Q1 due to the other charges, plus Q2 times the voltage at Q2 due to the other charges, plus Q3 times the voltage at Q3 due to the other charges. So you have to understand what V1 is. V1 is the voltage at Q1 due to the other charges, due to Q2 and Q3. G2 is the voltage at Q2 due to the other charges. V3 is the voltage at Q3 due to the other charges. The thing with this pattern, it shows up with 3 charges, but it will show up regardless of how many charges you have. Even if you have n charges, the pattern still holds. So for n charges, W is going to be half, and you take a sum from 1 to n of the charges time the voltages at each charge due to the other to the other charges, right? And this is the total energy of the constructed field in joules. Okay, so this is the total field energy of the field due to the charges that construct the field. This is the perspective. All right, so this is a pretty general formula. Let me see. But this is always true. This is a way, so I have a bunch of charges. This is a way to determine the total energy in the field by considering how those charges are constructed, how those charges are configured. How did they arrive at this configuration? An amount of energy needed to come in to build this configuration, and that energy is the total energy that's stored in the field. This is the perspective of looking at the energy of the field through the work required to construct the configuration of the charges. There's another perspective where we tie energy to the field itself, and we can also do that, but that requires a bit more calculation, and we will do that next time. But this is one way of doing it, and this is the starting point. By the way, although this gives me energy in joules, you have to consider that for EM fields, joules is a large unit. Unit that's more used is an alternate. It's a large unit of energy. There's an alternate unit of energy that's very popular in EM fields and in really high energy physics, and it's the electron volt. What is the electron volt? It's just another unit of energy. The electron volt is the energy needed to move an electron from infinity to point of 1 volts. Okay, the idea is that, hey, you have your space, you have, I don't know, your charge distributions, whatever, you know, Q, rho, whatever, and those generate some electrical field, E. Right? What is the energy? So at point P, let's say you find a point P that has a voltage of 1 volt. Okay, so you have your space, you have some energy distribution, but that doesn't matter. You need to find a point that has a voltage of 1 volt. Or you can build it. You can put a single charge, and you find a point that has voltage of 1 volt. So V at P equals 1 volt. The 1 electron volt unit of energy is the energy required to move an electron from infinity into that point that has voltage 1 volt. That amount of energy is called 1 electric volt, 1 electron volt. So how do you tie it to joules? When 1 electron volt, right? So so you know that the voltage is 1 volt here. So the energy per unit charge is going to be 1 joules per unit charge to get a charge from infinity to this point. What is the charge in this case? It's the charge of the electron. So it's 1.6 times 10 to the power 19 coulomb. That's the charge of 1 electron times 1 volt. So 1 electron volts is essentially 1.6 times 10 to the power minus 19 joules. Okay. Can we tie this to capacitance? Remember, we studied capacitance last time. So let's say instead of a bunch of charges in space, we have a bunch of objects. And those objects, we know how to calculate their capacitance, right? Those can hold charge. Let's say conductors, right? We know how to calculate their capacitance, C1, C2, the ratio of their charge over the voltage, C3, C4, and then I have infinity. I can use the lumped model and can draw this as capacitors going to infinity. I'm lumping everything together, right? So the idea is just to show, let's say you don't know charges, but you have a bunch of objects and you know their capacitance. What would the energy be? Well, to know the energy now, because you know the concept of capacitance, you don't only need to know Q. You're not required to know Q. You could, if you know V, that's enough, right? Because now V is tied with Q using C. So W is half some I equals to N of QI VI. Now I have this relationship between Q and V, which is Ci equals Qi over Vi. That's the beauty of capacitance. It establishes this connection between V and I. So I can rewrite W. Let's say I know the voltages for each object, but I don't know the charges. Well, then I can say Qi equals Ci Vi. So I can say the energy equals half I from 1 to n, and instead of Qi, put Ci Vi. So this becomes, I can take Ci Vi squared. So I have an alternate equation for the energy that only uses the voltage. Say I know the charges for each object. I don't know what the voltage is, right? So I know that Qi equals right. So I know that Vi equals Qi over Ci. I know the charges, but I don't know the voltages. So I re-plug it into this equation. And I get half I equals 1 to n. And instead of Vi, Qi over Ci. So this becomes Qi squared over Ci. Okay. So this is the equation that we've established. W equals half sum I equals 1 to n Qi Vi. Let me write it in this form. This was established only for point charges. So I bring in n number of point charges. The question is, how do we deal with charge distributions? How do we deal with charge distributions? So with charge distributions, we have to do the calculus thing again. We have to divvy up the charges into small segments. So I have, say, instead of in my configuration, instead of having a set of n point charges that I used to build up the field, I have a charge distribution. I have a certain volume. I have rho v, a charge density at every point in space. And then I have a small volume element here, dv prime. And then this volume element has charge rho v dv prime. Okay. So it's the same thing, but now here we don't have n approaches infinity. So n approaches infinity, and then each Qi is going to have a charge of rho v dv prime. So now I am summing an infinite number of things, right? But each charge is getting smaller and smaller and smaller. So hopefully there's a limit there. So I can turn this sum into an integral. So W is going to be half, and now I'm integrating across the whole volume of the charge distribution. And then the charge now is rho v dv prime. That's the charge. What else do I need? I need the voltage at this point due to the whole charge distribution minus this element. Well, this element is infinitesimal anyway. So the contribution it does to the voltage approaches zero anyway. So anyway, the voltage of the configuration itself at this point is really the voltage of the whole thing minus this really infinitesimal segment. So the voltage at this point is really just the voltage of the configuration itself, right? And this is the voltage that you calculate for this configuration. So this is now the integral form of this relationship for a distribution. It's going to be just rho v dv prime, right? So this is for a volume distribution. What about the surface distribution? So a surface distribution, you have a surface, S prime, you have a small element here, ds prime. the charge of this small region is going to be rho s ds prime. And the same thing, you sum over this surface. So W equals half s prime. The charge is rho s ds prime. And then the voltage at this point, due to the whole of the surface minus the voltage due to this infinitesimal element, is just the voltage, right? Because the voltage due to this infinitesimal element is zero anyway, because it's infinitesimal. This surface shrinks to zero. What about the line charge? Rho L. Same thing. W is going to be half L prime rho L V. But anyway, I mean, the most general thing you can deal with is 3D space anyway. So you have, now we know the energy, total energy of the field, how it relates to the charges. This is half integrate over all the charges, whether they are volume or surface or line. Assume they are volume here. Find the charge at each infinitesimal element, which is rho times the surface or volume or line element, and then multiply by the voltage. Right. So this ties energy to the charge distribution. This is correct, but we said we can go further. So this is absolutely correct, and you can use this. But we want to go further. Here we tie W to the charge distribution. Is there a way to forget about the charge distribution and just tie W directly to E? So if I know E in space and correspondingly V, so if I know V in space or E, V or E are the same description of the same thing, right? Are different descriptions of the same thing. If I know the electrostatic field, can I directly find W? Here we can find W, but the site's tied to the charge distribution. We have to know the charge distribution. It turns out, yes, you don't need to know the charge distribution, because the energy ultimately is built up in E itself. So you can tie W or calculate W from the field distribution itself without knowing the charge distribution. So we're going to go through this calculation next time. Let me see if there are any